Okay, good morning again. Let's talk about the last topic of my role here, but it's a very relevant topic. If you were taking a course like this 20 years ago, or probably even 10 years ago, people might not teach you dynamic compilation. Even if they would not be able to speak about it so highly, but it has become very relevant in today's world where we have most languages. We have seen examples, multiple examples over the last 2.5 days where we said that providing good abstractions helps programmers, but it also incurs costs. And nowadays it's the world of providing higher and higher level abstractions to programmers. In fact, programmers are non-CS people, as we had discussed primarily nowadays, and languages have gone even higher level. It has gone to even that level that you just want to write English and you just specify English and a software called as ChatGPT gives you a program, maybe correct, maybe incorrect. But think about it this way. Most people in the upcoming days will not write programs in low level languages. They would write programs in very high level languages like in English, let us say, or maybe some GUI like languages, let's say, visual languages, and or even spoken languages, whatever. So they would specify things at a very high level, and then code written or code generated in those high level languages cannot take advantage of the hardware, cannot take advantage of the machine. It doesn't know about it much, and hence the role of a compiler for such languages becomes even more important. Okay. So let's start by just recapping the advanced material we have learnt about till now. Well, we started with basic things, but then we went on to backend. You have learnt about data flow analysis, you have learnt about SSA based optimizations, peephole optimizations. So starting from basic fundamental passes of a compiler like scanning, parsing, IR generation, you have also seen optimizations that the compiler does, machine independent as well as machine dependent optimizations. Then we looked at code generation, register allocation, scheduling, pointer analysis, memory optimizations. We have seen a glimpse of many of these over the last 1 week almost. Today is the 7th day, right? Yeah, so over 1 week you have seen a glimpse of many advanced topics in compilers. You will see more. You will see loop optimizations, parallelization, code generation for multi-core and GPU hardware and so on over the next few days, which covers a big, vast amount of advanced material about compilers in this winter school. And we also learned all of them additionally for O languages with some programming assignments or practice for Java in this case. So now let's talk a bit more. Even though dynamic compilation is not specific to Java, in fact it's more popular for languages like Python and JavaScript nowadays, we would look at a representative example. Java was one of the most famous languages to introduce dynamic compilation, and a lot of advances in this compilation exercise happened due to evolution of Java runtimes over the last few years. They have been adapted by other languages too. So we would, and since you have learned a bit of Java in this course, we'll talk about it from Java's perspective, or we'll use Java as the case study basically while studying about dynamic compilation. Okay. So you understand Java's translation mechanism more or less. Java programs are translated by JavaC to .class files. You also know how to see the contents of those .class files, bytecode and so on. And then we say that these bytecodes can be sent to any other machine, any other physical machine with another architecture where you have a Java virtual machine installed for that architecture, and this JVM basically is responsible for executing the programs in the bytecode format, right? So we haven't really looked inside the JVM in detail yet. This blue box over here is something we would look at now. Okay. Java, in order to get a full picture, JavaC does not really perform many optimizations. It cannot perform machine dependent optimizations first of all, because it doesn't know about the machine. The code it generates is platform independent. But we have something inside this box because of which typically JavaC does not even perform many machine independent optimizations. It does not perform any iterative data flow analysis or any other. It does some basic constant propagation. It does some type checking before generating IR. It throws errors. It does some initial stages of a compiler, but it doesn't optimize your code much because the expectation is that all of that will happen inside the JVM. Okay, but this was not really the expectation before. In 90s when Java was introduced, This is how it was. This blue box was just an interpreter. Okay. And I hope all of you would agree that interpretation would tend to be much slower than compiling code to a faster binary and then running that binary. Interpreters don't have access to the whole program, just one instruction at a time. They cannot optimize their analysis scope. Even if they were to do some analysis, is just one instruction at a time of the language they are working with. So if you are working with Java bytecode, if you are interpreting Java bytecode, you only can look at one bytecode instruction at a time. Right? You have to execute it, give the effect of executing it immediately. You don't have time to look over the whole program, or even two instructions in this case. Okay. So Java C doesn't perform many optimizations. What happens? Well, as I told, the reason is it cannot perform machine dependent ones, and machine independent ones as well. They limit them to what happens in the VM, as we would see now. So there is a reason. Compilers like Java C, a technical reason dependent on the language, Java in this case, because of which even if Java C we were to load Java C with many optimizations like GCC, for example, or we would be in trouble. Let's see an example. So C is, for example, much less dynamic. What do we mean by dynamic? We'll see next. But C or C++ are much less dynamic than Java. Similarly, Java is much less dynamic than JavaScript or Python, for example. So what do we mean by dynamism here? One is, some of you mentioned yesterday, one is that you don't have type information in JavaScript or Python, but you have type information in Java. Java is not a dynamically typed language. In fact, it's more statically typed than C or C++. So then what do we mean by this dynamism here? We claim that dynamism prohibits useful static optimization, but you would find it to be true for dynamically typed languages. You can't even figure out what is A plus B without knowing the types of A and B. But what about a language like Java, which has actually a stronger type system than C or C++? Why do we say what dynamism prohibits static optimization here? Let's look at a few examples. Okay. There is a feature in Java called as dynamic class loading, for example, and this feature derives again from the history. When you remember, we mentioned yesterday that when Java was designed, it was the advent of the internet as well. People wanted to transfer code here and there. There were long running programs being invented. Servers were coming in to maintain all the big internet infrastructure and so on. So that was the time when people wanted to have long running programs that can be modified over time as they continue execution, and they wanted to send the modifications over internet. Dynamic class loading allows us to modify a running program in some sense, as we would see now. For example, let us say I have this piece of code statically available. I give this to Java C and expect that Java C would perform some optimizations as well. What would happen? Let's say I have a method M here which calls bar, checks if bar returns 0. If it does, then it launches a missile. Otherwise, it doesn't. So now what happens here? What does bar return in this case? Does it return 0? It depends on what is the return value of foo here. What's the static type of X? A. So it depends on what all can be pointed to by X, which foo can be called here. In this program, what all types of objects can, or what all method implementations of foo can be called here? How many implementations of foo exist in this code? Only one. So then let us say Java C sees that, oh, I can statically link this method foo here. Since there is only one possibility, X is of type A, and there is only one foo in the class hierarchy A, nobody extends class A here and overrides the method foo. Since it's only one, Java C decides to do interprocedural analysis and optimization and decides to inline that foo over here. You know that inlining a method may increase the scope of analysis. You may be able to perform better constant propagation here. If you inline this, you would be able to say 10 plus 10 is 20. Let's say you inline this also here, or even if you don't inline the return value of bar, let's say you can figure out with an interprocedural analysis that it will be 20, which means the Java C compiler may perform another optimization here. After inlining foo, it may remove this branch over here. And what should it do? If it removes this branch, will this condition be true or false? False. So it generates code, optimal code, which doesn't have this launch code here. Okay, fine. And it does. Maybe there is more code here, which it does, but it doesn't launch a missile. That's the code generated for the method M. If I perform optimization statically using Java C. But now I have a feature called as dynamic class loading, which can make life different. While my program is executing, let us say over the wire or somewhere, I supply a new class B. See, programmers can implement classes independent of each other, right? This program is self-sufficient on its own, and if I create a new class B that extends A, I give the path of A, they can be in different files, doesn't matter. So I supply a new file containing a class B that extends class A and overrides foo. And now there might be some code that calls this method bar by supplying some objects here. Since there are only A type objects available earlier, that's okay. But now let's say I have class B, so the main method starts seeing some class B objects now, and due to under some condition, it also starts passing class B objects to bar. Now the JVM, the Java C compiler, let us say, statically optimize this code to assume with an assumption that foo always returns 10, which means you can remove this branch over here. But if I supplied a B type object over here, what would happen? So can I continue execute? The question is, can I continue executing the previous code if I load this class dynamically into a running program? Because what may happen now, if this foo can be called over here, the return value will be 0. If the return value will be 0, what should have this condition evaluated to? True. Yeah, 10 plus minus 10, 0. So if it was 0, this condition should have been true and the missile should have been launched. Or forget missile, we are not attacking anybody. Let's say the rocket, the next satellite might have been launched. And now people waited 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Nothing happened. Right? That is still okay. Maybe just media will say bad words. But what if it was the other way around? What if there was a war and this was not equal to 0? The Java C compiler inlined this method, assumed nothing would happen, and actually it leads to a launch and of an attack. The whole world, one compiler bug may lead to the whole world getting destroyed into a third world war or fourth world war if you count the current one as third. So it's a problem. The idea is static optimization of code in presence of features like this may cause big problems. Okay, you can't really afford to generate code and execute it, continue executing it if some assumptions made there may go wrong. Well, from the compiler's perspective, there was no assumption. This was the program. But if your language has a feature like this that allows you to introduce new code into the system on the fly, which was popular for Java-like languages in the 90s, as we established just now, then we are into trouble, right? So if class B gets loaded dynamically, statically inlining foo into bar and possibly that bar into M may go wrong. It may make the program behave weirdly, and that means static optimization should not have been done in this case. We also have other features. There is a feature called as reflection in Java, which allows us to read class and method names as programmer inputs, as strings, let's say, create instances of those classes, call methods of those classes, inspect values of their fields, and so on in the program, right? So if I have, let's say, a program like this, I have an interface game with a method play. There is a cricket class and the soccer class which override this method play. They do something inside, and now I can write code like this in Java, which says, oh, get a string argument to a method M, search for a class with that name C, which is the string here, get an object of that class. We had said for each class we have some metadata, right? That metadata is stored into a class object. CLASS class object with capital C over here. So there is a class object associated with each Java class which stores metadata information. I could create a class object like this using this reflection feature in Java. Then I can find a method with name play and no arguments. That's why there is a null here. Otherwise I'll supply the type of arguments over here. I can search for a method called play with signature like this in that class. if I find a method like this, I need a receiver to call a method, right? If I have a method play in class cricket, I need a receiver object of class cricket. I can create a receiver of that class, a new instance of that class like this, again using reflection, and I could say method dot invoke obj, pass the obj here, and invoke internally is a library call in Java which will do something like obj dot method. So it will call the method using the receiver obj, which means you can take the name of what game you want to play here as argument and decide to call either cricket's play or soccer's play based on programmer's input. Now what will the programmer supply? We don't know. So what if again I was trying to perform inter-procedural analysis, for which I need to know the targets of method calls. Here the static compiler like Java C may know very little, or it may not know anything about what is called over here. Here maybe it can see that, oh, there is a play method, so only those classes methods are candidates whose name is play and the methods whose signature matches what you have supplied here. But what if the name of the method was also taken as a user argument? Then what would a sound compiler do here? If it was trying to perform any inter-procedural optimization here, what would you say soundly? What can be called here? Anything. The whole world can be called here. You don't know which class, you don't know which method. So if you are doing any optimization, you would end up doing a futile effort, because at this point you would not know what happens after this, which means you have to assume anything can happen after this. The whole program can be, all the parts of a program can be executed from this point. If you have this at the top level in your main method, let's say somewhere, you don't know what does the program do. Static compilation is a wasted effort. You can't do anything. Templates are different. Templates are not right. So don't get confused between this angular bracket. These are generics. They have nothing to do with reflection. Reflection is the capability of inspecting a class, accessing its fields, creating objects of that class, calling methods of that class based on arguments taken at runtime. Okay, it's very different from templates in C++. That's different. All of you with me? So this again is a feature that inhibits static optimization. We can't really do much if such a feature exists in my program. Let's look at one more. There is a feature called as hot code replacement. How many of you have used debuggers? Any debugger? Which one? GDB? Anything apart from GDB? What is that? Oh, for LLVM. Yeah, okay, sure. So for LLVM there is a similar one. Any others? And has anybody used a debugger for Java? So many debuggers, what does a debugger allow you to do? It allows you to pause a program and inspect its state. It allows you to read the values of variables and so on. Many debuggers also allow you to change code on the fly and see what happens. Oh, there is a statement a equals to 10 where you pause, where you put a breakpoint, and then you can figure out what are the values of other things here and do something. Many debuggers, at least Java's debugger, allows you to even change the program and say, oh, a equal to 10, let me change it to a equal to 15 now. And then let me see what happens in the remaining program, because I am trying to debug, I am trying to see what values are leading to a crash, for example. So I can allow changes in my program as they execute as well, right? That feature is called hot code replacement, and what happens is you can basically modify code during program execution. So again, if this was my code, my compiler was happy. Oh, let's say I disable dynamic class loading as well. My compiler is happy, this is the program, let me optimize statically, give some good results, let me not depend on the runtime much. But what if I use this feature HCR, hot code replacement, to at the runtime change class A's foo itself. Instead of return 10, I change it to return minus 10. If I do that, and if I would have analyzed foo beforehand over here, would it be right again? No, again a missile may get fired or not fired depending on what happened after inlining, and my program may behave differently. So there are again features like this that inhibit static optimization. If you statically generate binaries by performing optimizations, those binaries may go wrong. And if you want to be conservative, then how much can you do statically? If you can't even trust that one line of code will remain same until runtime, what optimization can you really do? Isn't it? So there are languages like Java, the beautiful language Java which we have been working with, that have a lot of dynamism for programmer flexibility, and that dynamism kills static optimization. Okay? So you can't really do much in Java C, and that's another reason Java C was not made very powerful. So now what happens? Are we doomed to bytecode interpretation? If Java C cannot do much and initially the JVM only had an interpreter, what would happen to Java programs? They would run very slow, and that's what happened in 90s. Java programs were known to be extremely slow. Oh, beautiful, oh, abstraction, no null, no seg faults, nicely thrown exceptions, platform independence, compact bytecode, easy to write code, but extremely slow, which people found to be the case with Python 5 years ago. Oh, lot of data science code in Python, big data, it doesn't work for anything. Very slow, right? So the same case was true for Java in the 90s. And let's compare how slow it could be. It's possible to just have an interpreter in the VM and see what happens. How slow it could be if you don't have a compiler for bytecode and you just have an interpreter. Let's look at an example, and we'll compare C++ with Java for a simple example. We'll also see if we just interpret Java bytecode versus we just run Python in interpretation mode, who is faster and so on. So we'll see some code execution here. Okay, just to understand what is the scale of slowdown that we are talking about if there was only bytecode interpretation being performed. So here I have a C file here. What it does is, there is a structure which has a field n and a field res. What I do is I take a command line argument in this C program. That command line argument is supplied to the value n here of the structure of an structure object here, and then the res is initialized to 0. What I do is, don't try to understand the code too much. In all this code, it's a random 3-level for loop doing some random computation. But what is interesting is, each loop executes until the value of n, starting from 0. So larger the value of n, longer this program will run, and I'll continue doing some random calculation which I print at the end. I'm computing object.res here and I'll print it at the end, right? Some simple program, and you write matrix multiplication, you write lots of programs that have those nested for loops, you write image processing programs. This is a very common structure, is what we can assume. I have an equivalent C++ program, same thing. Instead of structures, I have a class here, the same for loop, 3-level for loop, initialize in the constructor the value of n and run them. I have an equivalent Java program here. I again take an argument and I initialize the value of n in the constructor, and I run the for loop until that point and print the result over here, system.out.println. Same thing. And for completion, I asked one of my students to also give me an equivalent Python code for this. Of course, it looks smaller, that's the attraction, but it also does the same thing. There is a self is this pointer in Python, and I store n into the command line argument n into it, and there is a for loop here. Which does equivalent computation. Okay, reasonably similar programs. And now I have a script here which compiles the Java program, the C program using GCC, no special arguments. This is the default for Java, default for GCC, default for G++. And now it computes the time. If I supply some number of iterations, those many number of times will each for loop be run for each of the languages, and I would echo the time taken by each of them. All of you with me on the example? It's a simple example. Don't draw inferences, final inferences that, oh, this language is faster than that one just by looking at one example, but this is a reasonably representative example, is I want to claim. So now let's run this. Let's say I do run.sh and I supply the argument 100 to it. Okay, so each loop will run 100 times for all the 4 languages. Let's see, how much time do they take? Oh, but what happened to the Python program? Why didn't it print for the Python program? Oh, it's not there here. Wait. I loaded a previous Vim session which loaded a file somewhere else, and hence this uncomment did not really kick into picture. Let's run it here. Run.sh 100. Well, the Python program took 0.5 seconds, C took 0.1, C++ 0.1, Java looks to be slightly smaller, but fine, very reasonable, very comparable times. Python is slower here, but let's strengthen our observations. Does it scale in the same manner? Let's make it 500. Python will block your productivity. 5.5 seconds, 0.3 seconds, 0.4 seconds. This last guy looks interesting still. 0.074 seconds. Now let me not waste time. Once I make it 1000, the Python program will take 45 plus seconds. I ran it at home and tried it. So let's just forget about it for now. Let's just comment it out and let's understand that Python is super slow, and then let's try to build from there. Why is it super slow? It's interpreted and it can't be optimized much. Well, there are JIT compilers for Python nowadays, but again, it's dynamically typed, it's challenging to optimize Python programs and so on. So let's limit ourselves to C, C++ and Java here. Just Python lovers, I have kicked your favorite language out. Okay, if we talk about performance without a JIT compiler. 1000, what happens? Oh wow, something is magical here. 1500. We'll see. You will answer the question by the end of the lecture. Favorite C++. Java still runs faster. What is happening over here? Let's try something else. Let's try, so now I don't know. It may happen that now it will run faster. O3 is small o or capital O? Capital O. Let's try the best we can do. Maybe it will run faster, I don't know. It did used to run faster for a certain version of C, C++ at least. Yeah, it does. So it beats a bit, but I haven't entered anything special here. If you allow me to enter O3 for GCC and G++, you should also allow me to enter some interesting arguments when I run Java here in the JVM. Okay, so that's not a fair comparison, but fine. You can see that it's still, without any special tuning, Java program is running faster than C and C++ programs here, much faster than the Python program here, and with some tuning they are comparable. 0.5 second, 1 second, not such a slowdown like 45 seconds and 0.5 seconds. And of course, if you allow me to play with this program a bit more, I will be able to probably scale up the Java program even more. Yes. Not all kinds. So the tuning also happens automatically in other compilers. I see this coming many times. There is a lot of tuning that you can do while you invoke the JVM as well if you know about the program. Right? And you can help the JVM do better things. Here. Like trigger JIT compilation at level 2 from the beginning for a given for loop. Right? Trigger optimization early on, for example. But anyway, we'll talk about it at the end. So you could tune your JVM also significantly here. And this is not just for this program. Java performance has become comparable to most C, C++ programs nowadays. People are writing compilers in Java now, which people didn't used to do before. From early 2000s, people have started to write systems programs in Java. In fact, I was telling our TAs, we were collaborating with a group who had written a compiler for the R programming language. Have you heard of R? Yeah, even more notorious than Python to optimize. So we had an interesting compiler for R written in C++, and now they are rewriting whole of it in Java because they don't think that they feel that it allows them to implement faster, easier, fewer bugs, and they are seeing the performance doesn't change much. It's still acceptable performance, right? So lot has happened, and since we were talking about interpretation, let's just close this example by doing one more thing. Let me just compare Java and Python, where Java is just being interpreted. If I supply -int here, it means don't do anything fancy in that blue box, just interpret like you would do in 1990s. Okay, so we can now compare performance even under this condition. Let's say 500. Yeah, so it's still expected. You remember the Java program took 0.5 seconds. This is expected as per the language's design, right? Well, both are being interpreted, but Java bytecode has type information. It can be optimized more than Python, for example, by default. So that's expected. I just wanted to show you that language features also have impact. So by definition, Java programs would take more time than C and C++ programs because you have nice type checks there, array bounds check, which will take some time. But a lot of advancement has happened, which can get rid of much of this cost. Okay, that's something we want to show. And of course, we'll talk about optimizations that a Java compiler can do inside the VM that C or C++ it's very difficult to do, for example. Probably not possible to do to that good an extent.
Sir, but all of this is for Java bytecode, right?
Yes.
It is not for binaries. C or C++ create optimizations for binaries also.
The JVM also does that. Yeah. There is nothing that a C++ compiler can do that the JVM cannot do, that you will understand by the end. Okay. So fine, we are, the idea is if I didn't put that accent, Java performance is comparable to the fastest programming languages out there nowadays, and what is the reason behind it is what we are going to learn in the next 1 hour roughly, maybe slightly less than that. So the reason is just in time or dynamic compilation. Different people call it differently. There is a minor reason why it was called dynamic compilation before, and then people in the Java community invented this word called JIT compilation. But you can assume that except for those historical reasons, they mean the same thing. Okay. So just in time compilation is responsible for giving performance to at least Java programs here, and what it means is you want to specialize your program to the current execution profile on the fly. Okay. You have some program generated by the Java C compiler, you want to make it faster in some sense or more optimized based on the current state of the program or the current execution behavior of the program inside the virtual machine. Okay, so you can say you want to specialize a program at execution time with respect to that execution instance. A just-in-time compiler has access to runtime profile. It also can specialize the program to runtime inputs. It knows what the programmer has given as the command line argument or supplied as argument to M. What is the value of that string there? What is the name of the class there? All of this is known at runtime, isn't it? C and C++, or rather the hardware doesn't interact with the C or C++ compiler at runtime, and hence there is no way that the machine can convey this information to a C++ compiler on the fly. Whereas if you have a Java virtual machine sitting in, why not let that Java virtual machine learn from the hardware about the program's current execution? It can give you information about runtime inputs, it can give you information about what code parts are being executed frequently, it can give you information about which parts are incurring more cache misses, for example. It can interact with the actual machine, collect a lot of information about your program, and give to a compiler that can on the fly optimize the program even more during execution. This whole process is called just-in-time compilation. All of you with me till now? Okay, so the idea is generate native code, binary code that can execute directly on the machine. So instead of interpreting bytecode, you can directly generate binary for that machine. You can perform machine dependent optimizations, and you can perform profile based specialization for that run of the program. The first part of course can be done by any other compiler statically, but the latter part cannot be done. And secondly, for a language like Java which has dynamism, you can't even do machine independent optimizations aggressively during static compilation, as we have seen in previous slides. Okay, so yes, so particularly for languages where you can't do much statically, JIT compilation offers a very good way of speeding up those programs. Okay. You won't probably benefit too much by writing a JIT for C or C++, or not as much as you would by writing a JIT compiler for Python, for example. And is it there in many languages? Yes, Java, Scala, Clojure, Kotlin, Groovy, all of these generate Java bytecode. All these languages are run on a Java virtual machine. Basically, you generate bytecode, and then there are multiple Java virtual machines: Hotspot, OpenJ9, Graal VM, Tornado VM. Which is there on your image? Can you guess the Docker image that you are working with? No, it's OpenJDK is the open source part of Hotspot virtual machine. Hotspot is Oracle's. Who was it before Oracle's? Sun Microsystems, right? Sun was the best deal that could have been made at that time was to buy Sun, and Oracle did it. That's why they are surviving till now. So I mean, Sun Microsystems developed this interesting language called as Java, and now Oracle develops its virtual machine, which is called Hotspot, right? So, and IBM has OpenJ9, Oracle has Graal VM, some independent people have written Tornado VM, and so on. So there are multiple Java virtual machines, like there are multiple C compilers, for example. And yeah, JIT compilation is not only popular in the Java world. C# family of languages use the .NET framework, a pretty much replica of what we have in, or very similar to what do we see in Java virtual machines now. Similarly, Python has the PyPy JIT compiler. Have you heard of it? Yeah, Python has so many people who fail to scale their Python code nowadays use PyPy. Of course, PyPy doesn't support full Python, but it does optimize Python programs significantly because it uses JIT compilation. JavaScript has V8, Firefox's SpiderMonkey, Apple's JavaScript core, all of them use JIT compilers to optimize code for your browsers. Lua, has anybody used Lua? A very beautiful language. A fun language to play with, right? So Lua has a Lua JIT, R has a Rush, this is pronounced as Russia, R has a Russia compiler, and so on. Okay, so there are so many languages that actually use a JIT compiler nowadays. Alright, so what can a JIT compiler do? Let's look at an example. Here is my code. I have a method foo that takes two arguments, one integer argument a and another reference variable called o of some type x. Class x is, let's say, extended by class y and class z. This is not valid code, I have just written it notationally to save space. Let's say x defines a method bar that returns 5, y overrides the method bar to return 2, and z overrides the y bar to return 10. So this is the class hierarchy. There are 3 bars here, and the static type of o is x. I have b equals a plus 10 here, so I can't perform constant folding here because I don't know what's a. A is supplied as an argument from the place where you call foo. If you call foo at multiple places, you may be passing different arguments everywhere. Similarly, you have o dot bars result multiplied by b stored into c, and then you return c. So which bar can be called here? All of them, right? Since o is of type x, x class reference can point to either an x class object or y class object or b class object, which means any of them can be called over there depending on the runtime object pointed to by o, right? So if you were optimizing this code statically, what optimization that you have learnt in this course can you perform on it? What will you do by pointer analysis? You will say that, oh, 3 bars can be called here. Then what pointer analysis is an analysis. The question is, can you perform some optimizations that you have learnt in this course on this code? Can you do constant propagation? No, there is no constant to propagate. Can you do folding? No. Can you do method call resolution? No. Can you remove that object? No. Can you do anything in this code? No. That's an optimization that we would in fact think of now. Yes. So just you would give a name to that optimization by the end of this or the next slide in fact. Yeah. So you could create multiple versions of foo depending on all the possibilities that are called at o dot bar. That's Jayasree's answer. That's something we will do in fact. But that's an optimization you haven't learnt of in this course. So you have been studying this course for 1 week, and for all those programming languages that we listed down there, you can't perform any optimization that you have learnt in this course. What to do now? Let's use a JIT compiler and see what could we do. Okay, you have this code here, and now let's say at runtime, my virtual machine observes the behavior of this program and says, oh, last 1000 times I am seeing that whenever somebody calls foo, they actually supply 10 as the first argument. And this is an input that the JVM has learned by just looking at the argument supplied to, recording and looking up making an analysis over what was supplied to foo with more probability. And let's say they find that, oh, almost 100% of times the value supplied is A. If the JVM can make a guess now that in future also highly likely the first argument supplied will be A, what optimization can the VM do now, or can the JIT compiler do now? Exactly. Now you start speaking. You can perform constant propagation now here, propagation, folding, whatever you want to call it. And with the assumption, let's say I record the assumption here inside that the remaining optimization is valid if A is 10. If A is 10, you can keep on doing more here. Now you can replace this A plus 10 with 20. You can get rid of this variable A. You got rid of this variable B, memory saving. See, it's a small example. The same thing works for a larger example. So don't think that if I say I remove two variables, that's a tiny thing. You can remove thousands of variables like this everywhere in your code. So I remove some variables here. I have removed an addition operation here, and I have folded the constant here to get a 20. Now, if I can observe what is A, can I not observe what type of object is O? Right? So let us say the VM again observes for a long time and tells me that, oh, till now I am just interpreting this code again and again and again, and while interpreting various calls to foo, I have observed that O dot type is always Y. Since I have been interpreting this, I feel it's taking lot of time. Hey, my dear JIT compiler, can you assume that it's always going to be O and give me some optimized code, right? The JVM places a request to compile foo under the assumption that A is 10 and O's type is Y. It requests a compiler thread to give a version of the compiled code for foo under these assumptions and says, give me a better code, I'll run it until I can. Okay, I'll switch over from interpretation, I'll run your optimized code under these assumptions. So now if we do that, what can the JVM do now? Which optimization from this course can you perform? If O's type is always Y, you can inline the method, right? You can statically link that method, and if it's a small tiny method, the cache size doesn't overflow, you can even, the cache block doesn't overflow, you can even inline that method. So you can say, oh, let me perform method inlining, forget about method call, vtable lookups here, I'll directly figure out what does bar do, it returns 2, I'll substitute 2 over here for the call to bar. Again, the cost of a method call is gone, and now can I do some more optimization here? Again, I can do constant propagation, right? I can, yeah, you could have done some shift operation, I don't know. Otherwise, you can just, let's say, perform constant folding here and you get return 40. Now, the JIT compiler, let's say, gives me a binary. It performs code generation, register allocation, selection, scheduling, everything, and it gives me a binary that does not perform multiplication, addition, that has got rid of few variables, few operations, that has got rid of a method call as well. It directly returns 40. I have a binary that under some assumptions returns me 40. This binary would definitely be faster than interpreting this code if checking these assumptions is less cost compared to all the or if the trade-off is in favor by doing all these optimizations inside. You can see even for this small piece of code, the cost of a method call, one multiplication, one addition, having all these variables is definitely more than checking that A is 10 and O's type is Y. There are just two condition checks over here with an and in between, for example. So you may not even check all those conditions all the time, right? So now you may be able to create many more optimizations because of this. Maybe foo is called somewhere else. You always know now that foo is just returning 40 every time. Let me assume it returns 40, get rid of the call. Let me do some more optimizations. If there is an if condition later, I can get rid of that if condition because I know the value is 40. I can keep optimizing. So there is a huge cascading effect. And let's say because of these assumptions, I am able to perform lots and lots of optimizations. My program becomes faster, which is what happens in a JIT compiler. Makes sense? You have, what you have done now, you have specialized this program with respect to the current execution, in which the observation is that, oh, most of the times A is 10 and O's type is Y. Okay. Now the compiler gave this binary to me, and let's say in future I am continue to running this program, and what the JVM has done is, instead of interpreting this code, whenever it sees a call to foo, it just uses the binary produced for this version of foo with those checks. Now at some point of time, let's say one of these checks fails, either both or even one of these checks fails. The first argument supplied by the user at some point of time is 20 now. What do I do now? Can I execute this code? No, missile may get fired. No, right? So I cannot continue executing the optimized code if any of the assumption fails in future. So if the assumption fails, what option do I have? What could I do? I got compiled optimized code. Do I just have that optimized code, or do I have some safe version also with me till now? You have Java bytecode still with you. If the assumption fails, oh, forget about this binary code. I'll go back, happily start interpreting my bytecode again, right? So keep around some version of code that's safer or that's safe. and start executing that code. Whether it's another compiled code that did not make that assumption, maybe you can create two versions of this code. Now let's come to code versioning, as Jayashree said. We can maybe, we can maybe create one version of this binary that has only one assumption, that o.type is y. Still, I would be able to get rid of the method call at least over here, and I may be able to perform some folding there. If I have another version that says, oh, just a is 10, still I may be able to do some optimization over here. And if one of those assumption fails, instead of going to the interpreter, I could have gone to that version itself, right? So again, the JIT compiler may produce multiple versions of the code here, depending on what it feels is useful, and you could get optimized codes based on it, right? So if an assumption goes wrong, by default you can just start interpreting bytecode, because in the bytecode you did not make any assumptions. Assumption failure, you go back to the original version, or you could even create multiple versions and switch to them on the fly. All this is done by typical JVMs nowadays. So this process, when you optimize something under some assumption, and after that assumption fails, you fall back to some safe version which did not have those assumptions, is called de-optimization. You optimize, now you are de-optimizing. Okay, so the process of switching down from optimized code into an unoptimized code is called de-optimization, and it's often a wasted effort. As you can see, if I optimize and immediately the assumption fails, it was a wasted effort, more or less, some wasted effort in compilation and managing some switching from this code to that code and so on. So that's why JVMs would not like to optimize all the code immediately. It's a good idea to wait for a reasonable amount of time to gain confidence on what is the execution pattern in this program, and then perform the optimization. Of course, we saw that if we de-optimize, we saw that we can go back to another version that was safer, let's say interpretation. Should I throw away the optimized version immediately? No, maybe after some time I again start seeing 10 as the first argument. The user came back after a coffee and remembered, oh, I was typing 20 instead of 10. Let me go back to 10. I read this debited some money from my account. I should have typed 10. So the user starts typing 10 again, and then the assumptions again holds. If the assumption holds, I don't even have to compile it again. I have a binary available with me. I can just reuse it. I can again link the call site to that binary which had made the assumption, which was optimized under the assumption, and be happy, right? Or maybe it's not coming back to 10. Maybe it's now always 20. Maybe I should just profile for a bit longer and see, oh, should I just create one more version for 20 now? Because 20 is a popular value now. So should I reprofile and find newer assumptions if the code is still hot? By hot we mean it's getting executed frequently. So maybe I can record more profile information and I can create one more version of the code in future. Makes like a good question. Or as we said, you can maintain multiple versions. Again, an interesting question comes whenever you design a system like this is, how many versions to maintain? Maintaining which versions will be useful? Should you maintain 100 versions for all possible values of A and B, and will that not bloat up the amount of memory taken by my Java process? So there are trade-offs here. Can you give me a suggestion on how do I answer this question? How do I find, let's say A equals 10 allowed me to optimize the code significantly, but now it's no longer 10, it's always 20. How do I decide whether I should create another version for A equals 20 or not? Okay, so empirical decision can be done, but for that you have to compile it, you have to store it somewhere and then run it, record more and so on. Can you give an answer based on what all we have been learning? Can you write an iterative, let me make it more straightforward. Can you write an iterative data flow analysis that tells me whether maintaining one more version, creating one more version for A equal to 20 will help? What would you have to do if you have to write a program analysis to figure out, or let's generalize the problem. Let's say you had to figure out which versions are going to be potentially useful for a given function. An interesting problem, right? Yeah, so how do you find if making an assumption will lead to more optimizations without empirically checking the code after generating code, let's say? Because you don't want to incur that cost, let's say, of actually generating code and comparing the performance. Can you have used the ideas of static analysis to do something there? Yes, but I could have analyzed statically something and told the VM, maybe you should try to create versions of this kind for this method, just by looking at Java bytecode in suit, let's say, like you did yesterday.
If that particular assumption converges fastly, quickly,
What do we mean by convergence of an assumption?
like we are doing the iterative analysis to find till the point it gets repeated.
Mhm.
Like if we are finding that point earlier,
Yeah, but I'm doing it statically. What if it takes some more time to converge? I didn't get your answer probably. But
I was just trying to like
so which assumption is useful? We were trying to say, how do you find out if a certain assumption would lead to more optimized code?
So can we go something like SSA itself,
Mhm.
have multiple versions, like assume these are the possible multiple versions and have common convergent points, and based on it we can perform optimization just like SSA, like dead code elimination, common sub-expression. Similarly, we can find patterns here and eliminate all those control flow parts and say these are the possible parts that
Could be. Maybe you should optimize for some sets of values and see which of them lead to better codes being generated. But can you do it statically? I would like you to keep thinking. I mean, at least one of my students is working on this problem. So I know there are ways to make progress here based on what we have learned in this course. Keep thinking. This is an interesting question for any system that supports multiple versions. Which versions will be useful? Can you determine it by analyzing the program ahead of time? Right, it's something similar, but let's say we don't want to run it really, we don't want to create all those versions before deciding this, for example. Think about it. Okay, so that's and then the interesting thing. So yeah, if we do that, we can have binary 1, binary 2, binary 3, how many ever binaries are useful determined by your future analysis, and based on that we could decide to maintain a few versions and switch over to them dynamically based on which assumption is valid at a very particular call site. Make sense? That's also something that a JIT could do.
So is it again greedy in nature here as well? We start with one version, we kind of come up with the heuristics, and then we see whether are we able to satisfy the heuristic. If not, we jump to another.
It's not really a heuristic, it's actually a representation of the actual runtime behavior of the program, right? If you think about it. The heuristic is not developed based on any guesses here. The heuristic it's not a heuristic in my opinion. I feel we are using the word heuristic for too many things here. We should not discredit the JVM designers by calling it a heuristic. You can say, but I think it's something stronger here. It's an approximation of the actual runtime behavior of the program. It is called dynamic analysis. So you have static analysis which approximates the behavior of a program without running it. Dynamic analysis approximates the behavior of a program by running it. Okay, and that's what we are doing over here. Dynamic analysis is not just heuristics in my opinion, but it can be argued. Okay. Anyway, so once we have that, as you can see here, all of this is extremely expensive, right? Some part of your code is being interpreted, then you keep on profiling, you keep on recording information while your program is under execution. There is some compiler thread that's waiting to compile. The JVM has itself in its own thread which observes these profile information, sends it for compilation, takes it back, keeps checking these assumptions. If the assumptions go wrong, again switch over. If an assumption goes wrong at a call site, maybe the caller method also might have performed more optimizations based on the assumption. So you have to trigger de-optimization for even more methods. All this is extremely expensive. So now an interesting point comes in, which is why to do it for everything. Let us try to optimize code based on how frequently it is getting executed or how critical it is for in terms of optimization and so on. So for example, the hotspot Java virtual machine, what it does is it starts by interpreting bytecodes. If you have your main method, the first instruction will always be interpreted by an interpreter inside the Java virtual machine, and then it identifies hotspots in your program. That's why the name hotspot VM. How would you identify hotspots in your program? What kinds of code structures in your programs will be hot in general? Loops may get executed again and again. A method may get called again and again. So let us say we keep recording how many times a method is called and how many times a loop is taken, how many times a package is taken. These are two important critical pieces of unit, let's say. If I identify, let me put a threshold now that, oh, if a loop is iterated over more than 1000 times, then let me insert it into a compiler's queue, a JIT compiler's queue. The JIT compiler keeps on taking entries. If it has multiple threads, of course, you can have multiple queues, or multiple threads can pick from one queue and so on. And they keep on picking up elements from their queue to compile in the background. Okay. While interpretation continues, your program does not pause, your program continues interpretation. Let's say you sent method foo for compilation, and after some time you have the compiled binary available under some assumptions. Next time somebody calls foo under those assumptions, you would say, oh, let me change the linkage here, let me not interpret the bytecode, let me change the jump address here to the point, to the entry point of the compiled code of foo. And that's how you dynamically change the link over here. Now you would execute a faster version of foo whenever foo is called, right? Similarly, hot loops are replaced on the stack. While a method is on the stack, maybe just you can replace some part of the method with compiled code. For example, a loop that's executed frequently, and of course you can keep performing more optimizations here. So there are different Java virtual machines, as we said. This is the architecture of the Oracle Hotspot Java virtual machine, which has one of these interpreters typically based on which version of the VM have you installed on the system, and it has not even one but two compilers, two JIT compilers, one chota, one bada, one more powerful JIT compiler, one smaller JIT compiler, C1 and C2. So the idea is, oh, if I can send things for JIT compilation takes time to do all of it, right? It takes time to compile code, it has to make assumptions. Let me make multiple levels of compiler even there. Let me make a smaller compiler that I will invoke if I see objects in my code. Let me make another compiler which I would invoke if I see a lot of loops in my code. I can implement different classes of optimizations in different compilers like GCC O1, O2, O3 for example, and set different thresholds or different criteria for sending code to each compiler. Whenever the criteria is met, let me send it to that compiler, which will hopefully optimize the code more for that criteria. Make sense? Very, very sound reasoning if you ask me. So there are two compilers, and yeah, we have answered all of this. There are in fact multiple levels of compilation. 0 means interpreter. If a code if a code method is at level 1 in hotspot, it means that you are compiling it purely with a pure version of the C1 compiler. There is not a vanilla version of C1 compiler which performs some invocation and backage counting. So it's like compile with C1 and keep on doing profiling like you do in the interpreter. Then there is another level, C1 with full profiling. Oh, why only count method calls and loop edges? Maybe I should start recording what is the type of the argument, what is the value of a branch. Can I speculate based on branches, or am I taking the true branch more often than the false branch? Am I calling x dot bar more often than y dot bar? Let me start making more interesting observations if the code is getting executed even more frequently. That's called level 3 here. And then level 4 is the C2 compiler, which performs many more optimizations. So if you open up any Java code, you would see this happening. So let's say we had this test.java here, right? This was our Java version of this code, and let me now Java, if I am right, this is the flag, print compilation. I'll find out if it is not the right flag, and test, and now let's apply the argument 1000. Yeah, that's the flag. It gives me some information that, oh, this constructor was compiled at level 3 at some unit of time 56. After some time it found some library method hash code crossed compiler level 3's threshold. Let's look at foo. We have our whole for loop thing was inside the method foo, right? So here it says foo at 32. What could this at 32 be? Can somebody guess? I am compiling foo here. I am also compiling foo here, but at 32. Can somebody guess what could this 32 be? Not version number. The line number. Okay. So we said we would count packages as well as method invocation counts at level 2. The C1 compiler at level 2. Now we have gone to level 3. So see here, well, if you open test.java, there is no line number 32 which looks interesting. The line number there is no line number 32 in this file, so it's not essentially the line number, but very close. Bytecode, the index, the line number or the index of the bytecode instruction. So let me, how can you see bytecode? Have you learnt it in this course? Yes, Java P minus C, what was, it was class A. Java P minus C and A. Let me see method foo. At method foo at 32, I have an iLoad, a load instruction for an integer. I load this pointer, I get a field of it, and then I compare for if greater than equal to. Okay, there are 3 if greater than equal to comparisons here. 1, 2, 3. Can you guess what is 32 then? What is happening here? I had 3 for loops inside. Each of them had a condition check, and there are 3 condition checks in this code. This is the third one. So what is this code belonging to? The innermost loop, right? So in this case, basically the JIT decided to optimize this innermost loop with some loop transformations at level 3, let us say, right? It tried to compile this loop, just the innermost loop, because the innermost loop is the hottest, isn't it? It's getting executed the highest number of times. So if you see in the user code here, all these initial ones were library methods. In the user code, the thing got sent for compilation, JIT compilation. The first thing was the loop starting at bytecode index 32. After some time, maybe it saw, oh, even the outer loops are getting executed too many times, and if I include all the 3 loops, there is nothing else in the function. The whole function itself is getting executed 2 number of times, and hence I can compile the whole method foo itself. After some point, it said, oh, it's continuing to get executed. It crossed level 3 threshold and it's still continuing to get executed. Let me compile it at level 4, which is my strongest compiler. First, let me compile the loop at level 4. Maybe if we ran this longer, we would see that the whole method will get compiled at level 4, and so on. So that's first part. You can see JIT compilation happening at different levels for this code here. It's loop as well as the method here. There is one more thing here. We compiled at 3, then we compiled at 4. That's okay. But then we again compiled at 3. And then there is something here, made not entrant. What is happening? When can we go down in the compiler hierarchy? We discussed it just now. When will you throw away level 4 code and maybe you come back to level 3? Some assumption went wrong. So this is a clear indication that it made some assumption. Well, we can investigate it more by looking at its own IR and so on, but let's not go into it today. But we made some assumption at level 4 which went wrong. So I went back to level 3 here. Then after some time, that level 3 code was getting executed again and again and again. So I again made some new assumptions and compiled at level 4. And you keep on seeing this interplay. Okay. I have printed compilation. If you print some more, there is some more argument which will allow you to even tell when did you switch to interpreted code as well, and when were you executing with some timestamps and so on. So I hope you see what's happening over here. Any questions? At least I hope you agree this is extremely interesting. Okay, so we saw a made not entrant there. There are 3 states possible for a JIT compiled code in the VM. In use means you have a binary compiled under certain assumptions and you are currently using it. Made not entrant means you have not deleted that binary, but the assumptions went wrong, so you have put it somewhere else. Nobody should enter this binary anymore. And after some time, the same binary may get converted to in use, or if the JIT decides that no, I am filling up my RAM, garbage collector is not able to help me, there is memory pressure, let me clean away the binaries which are not made entrant for a long, which are in this mode for a long time, in this state. It's like a finite automaton here. If it's in this state for a long time and there is memory pressure in the running Java program, it may make it zombie. Zombie means the garbage collector can delete it. So in future you may want to again recompile, but right now I should throw away because my program is facing a memory crunch. All these decisions are made possible because of a Java virtual machine sitting between your hardware and enclosing a compiler. All these decisions can be made at runtime during program execution. Okay. Anyway, so I'll not go into the details of these. There is an interpreter with a huge switch case, which is of course expensive. So each bytecode, what do you do, push something to the stack, pop something on this from the stack, and so on. So there is an interpreter which does not perform many optimizations. It actually is quite slow because of comparisons. For every bytecode it has to find where to go. There is also a clever template interpreter that avoids this switch case. It goes over the next bytecode almost free of cost. So, but it's still interpretation. Then there is the C1 compiler. Now I'll just list down what kinds of optimizations it does, and I hope many of those you have learned and heard about in this course now. So C1 compiler is the low level, smaller, tinier compiler in Hotspot. It targets fast compilation, does not perform all kinds of optimizations that we have learned. Still it performs method inlining, dead code elimination, it optimizes call sites, constant folding, peephole optimizations. It uses a linear scan register allocator which is faster, for example, and so on. All these you have studied, and in the Java world, Java-C won't do many of these, but the JIT compiler can do. And its threshold is usually 1000 to 2000. If some code is executed these many times, it will be different based on some more heuristics, how to decide the threshold, and then it will be sent to the C1 compiler for this time heuristics is right. Based on this, it will be sent to the C1 compiler. Then there is the C2 compiler, which targets more and more optimization, compromises on the time taken for JIT compilation. It would do more expensive optimization. So apart from those in the previous slide, it would also do escape analysis. It will eliminate those null checks which we said are not required based on pointer analysis results. It will unroll loops. We will learn about loop transformations tomorrow. It would do some branch prediction at the compiler level. It would use graph coloring based register allocation instead of linear scan, and so on. Okay. It would also do some more speculative optimizations as well. Alright, and its threshold is usually very high. You want to incur the cost of performing all these analysis and optimizations only if the method is executed, let's say, more than 10,000 times. Again, since these are heuristics, these can change very easily. In the OpenJ9 virtual machine by IBM, they don't have a hard threshold like this. They identify it based on percentages. Oh, is the method foo taking more than 10% of the execution time of the whole program? Then it's a hot method and I'll send it for compilation, for example. So these are, of course, heuristics which different people can play with. Nothing interesting there. Nothing too interesting there. So yeah, we already saw a demo that shows tiered JIT, how it went from one level to another and it came back to another level. So there are multiple tiers like this here. In the OpenJ9 VM, the tiers are named differently. They have a single compiler because see, there is a problem, right? C1 and C2 are two compilers. They have their own IR. If some optimization is done by C2 as well as by C1, you have to re-implement it in C2. The code base becomes difficult to maintain. So OpenJ9 people forked out from Hotspot several years ago, and they went a different way. They said, oh, we won't have two different JIT compilers with different IRs. We'll just build multiple optimization tiers in the same JIT compiler. And they have optimization levels like GCCs, O1, O2, O3, OFAST, whatever. They have cold, warm, hot, very hot, scorching. These are the levels at which your code can be based on how frequently or how much time is it taking in relation to the whole program's execution. Based on it, they will decide how much to optimize that code. You would see compiler people are very funny. If you really open compilers, there are words like zombie used inside, there are words like scorching used inside, and so on. Compilers people like to keep their life fun. Okay, there is also another effort here which is the Graal compiler. You should know about it since it's a very popular effort. It's a separate Oracle project that decided that, oh, from last 10-15 years we are improving Java. Let us now write, we are compiler designers for Java programs. We are writing our compiler in C++. We have to learn two languages. It's problematic. We get confused like what I told you about last time. Oh, whether the initial value is null or whether it is garbage. We make mistakes. Let us just learn one language well is what they thought. So they created a separate project in 2013 or something, called it Graal, and they said now we'll write a JIT compiler for Java in Java itself. And since Java works fast enough, our JIT compiler will work fast enough. And that's a very successful project. If you install Java now, from Java 17 onwards, Graal ships into your JVM along with the C1, C2 compilers. You can switch to Graal instead of C1 or C2, I believe. Yeah, so it brings in, it allows research for Java community to happen more easily. and it implements more optimizations like this. It integrates with ahead of time compilation as well. Oh, can you optimize some code ahead of time, integrate with it? So they have been able to come up with newer implementations or more powerful optimizations, since they have an easy to write compiler now. And yeah, they are trying to replace C2 with Graal. A VM that has the Graal compiler is also called where it's the default compiler, they also ship it as Graal VM, which you can download and use. And then there is also a vision there which says one VM to run them all, like Lord of the Rings, one ring to rule them all. This one. So what it does is it allows you to define a language's semantics in some format. It translates those semantics to create a compiler, a JIT compiler for that language, and it allows you to run all these programming languages on Graal VM itself. So nowadays you might have heard of LLVM, which is many languages translate their code to LLVM and then get advantage of the LLVM backend. Similarly, there is a way to compile all these languages and run them on a Java virtual machine and get advantages of all interesting developments that have happened here over the past 5-10 years. So this is again an interesting effort that's going on. Our version of Graal VM at some point of time a few years ago, its performance started beating the default R compiler that GNU people had developed. So a very popular route for some programming languages. It's also a useful approach for something called as C. It's the last session, so I can throw some terms without expanding more on them for you to learn about more in future. There is an approach called as polyglot programming. Polyglot programs are those programs that use multiple programming languages within an application. That's becoming popular, right? Oh, you fetch data from a database using a Python script, or you float a server using, let's say, some Java code, or you write all the mathematical computation behind in C++, and you want all these to work together. So such kinds of approaches also help there, because all those code bases can finally get translated to a common platform. You could optimize them in a common manner across languages inside this and then run it on given hardware. Any questions? No questions? Is it okay? But I don't see anybody sleepy. Why are you not asking questions? You're just happy. Okay. Anyway, so most time, if you notice, there is one big problem over here, right? The time spent in JIT compilation directly affects the execution time of the program. So it's all so beautiful, but then it's costly. Whatever you do inside a JIT system is costly, right? You are snatching resources from the running program in some sense. So most JITs perform very imprecise program analysis. They won't do interprocedural. Most JIT compilers will do just intra-procedural analysis because it takes time. They might not perform IDFAs. They might just do flow insensitive analysis because again it takes time. So many JITs choose imprecise analysis and lose opportunities for optimization because of this fact. Hence, this question always comes in, will GCC-03 beat standard JVM invocation? Because JVMs, even though they have access to runtime profiles, they can speculate, they can de-optimize if assumptions go wrong, but will they be able to perform strong, powerful program analysis within themselves? So, or a general question, how to bring decades of advancements in static program analysis to the JIT world? Oh, we learn about so many things for static compilers. How can we make sure their benefits come in presence of all these dynamic features, everything, to the JIT compiler world as well? So these questions, this is the question we are trying to answer. I'm trying to answer this question from last 12 years now, since I began my research. And we have been quite successful over there. It looks a promising direction. It floats lots of research problems, like it allows us to develop newer analysis algorithms that are more efficient on a JIT compiler, ways to new ways to enhance precision of what a JIT can do. Oh, JIT doesn't have time to do everything from scratch. So why can't we do something statically and allow the JIT to improve on it instead of having to build from scratch and incur a lot of time? Can we reduce JIT's overhead? Initially, think about it this way. When you run a Java program, initially nothing is JIT compiled, right? Everything that becomes hot will be compiled for the first time. which incurs a warm up. Till that time, it's just interpreting code. So if you run a program for a long amount of time, you would see a typical behavior. Let's say vertical axis is time, horizontal axis is the number of iterations of a program, how many times you're running a program inside it. Let's say put a big for loop inside it. You will see that initially it takes more time than when it starts JIT compiling something, it may take even more time, and then it falls flat, because finally most interesting things have been JIT compiled. But this initial period is slow, particularly for languages like JavaScript, where you're running code on the browser. Initially, the first time you load a page, it might load very slow. All this is related to JIT compilation stuff. Okay. After you interact with the page for a long amount of time, it may become more responsive, because it has learned where all are you clicking, what functions are those clicks leading to. It has JIT compiled all that code inside the V8 engine, for example. So all these things happen under the hood. Can we do something to reduce that warm up time in the beginning? Can we reduce the slowdowns caused by de-optimization? If you de-optimize, you would see, oh, it was running slow, and suddenly there is a spike because it caused a lot of methods got de-optimized. So it became slow again. Oh, my program was running nice, suddenly it's slow. Oh, now it's again fast. How do you get rid of these unexpected slowdowns? These are interesting research directions as well. Reducing the overhead of profiling and de-optimization, performing newer optimizations that you cannot do without speculation. Can you figure out newer optimizations that you can perform because of the availability of assumptions that you can make, for example? Handling more dynamic features, we talked about them. Frameworks to optimize modern dynamic languages. So if you are interested in all these kinds of questions, there is a lot of work happening in our group at IIT Bombay. Our group is called Compel, and it's part of the Plateau Lab. We are doing a lot of interesting effort in optimizing Java programs, JavaScript programs, R programs, Python programs, these 4 representative languages for now. We have also worked with Scala for some time, which also runs on the JVM. So there are all these interesting questions we are working on, and this leads to the conclusion of the talk or the course from my side. So there are all these interesting things that we do. We are also working on some newer Java features like value types. We started working on the feature value types before it was released. So we are quite ahead of time in the way we do just-in-time research. And we also do something interesting here. This last point is very interesting. 3-4 years ago, what we found is when students start working on compilers, they struggle a lot to understand the internal working of that compiler. So fine, we have debuggers for general programs. How would a debugger look like if it is designed for a compiler? Can you debug these different things that happen inside? Can you understand them more easily? So we started working on this, and we have come up with a couple of interesting debugging and visualization tools for customed to compilers, which show you, oh, what state is a method in at this point of time, what led to this de-optimization. It allows you to understand it better. So it makes our own life, people who work in compilers, easier and more cheerful. So that's also something we have been working on. And we publish in top venues, but we also make sure that almost all of our work goes into industry compilers and runtimes. Harder life, but more accomplishment at the end of the day, or more satisfaction at the end of the day. Okay, and there is no lack of funding in compilers and lack of exposure in compilers, as everyone who will come and teach here will tell you. Okay, so there is a lot of interesting work happening in the domain of compilers and programming languages. Okay, if you want to learn more about any of this, you can go to my website, find out some interesting videos, or talk to any of the students. And I hope some of you would take up compilers as a career in future, motivated by this school. Irrespective of whether you do that or not, I'm sure you find these problems interesting, right? Lastly, since you are not asking anything, question of the school from my end. Which programs are the fastest? Python, C, C++, Java. 4 options, KBC. How many of you say Python? Get out of the class. How many of you say C? Yes. How many of you say C++? How many of you say Java? All of you are wrong. Why? Oh. Assembly, nothing. All of you are wrong. Why?
Because of the context we're working on.
Not just the context. Who makes the programs fast? Design a better compiler, come up with novel innovation, that language's programs will run faster. It's not dependent, it's dependent on the language to some extent, but it's dependent on the compiler to a much larger extent. Anyway, so who designs compilers? You, people like you. So now you are right. It's you who will make programs fast, hopefully. On that note, let's finish here. Thank you. Any questions before we break for lunch? Yes. Pardon?
This question stems from an earlier discussion we were having. I would like you to comment on application of JIT compilers in an embedded setting, because from what I understood, we are enabling more optimization, obviously, but that optimization does not come as a freelance as of now. Meaning that